Hi everybody. Yeah, me again. I've been looking at a 2018 puzzle from Advent of Code because I realised it was really quite interesting from the point of view of having to trying to solve this in COBOL. And let's just have a look at it and hopefully you'll see what I mean. So we have here a lot of stuff which just provides a bit of a background for the story. Don't need to look at that now. And then we get to this bit here. This is the first puzzle. And I solved this once just to, well, it's quite easy to do. And then part 2 gets much more difficult. So let's have a look at part 1. So let's start. After you're feeling like you've been falling for a few minutes, you look at the device's tiny screen. Error device must be calibrated before first use. Frequency drift detected. Certain. Cannot maintain destination lock. Below the message, the device shows a sequence of changes in frequency. Your puzzle input, a value like +6 means the current frequency increases by 6. A value like -3 means the current frequency decreases by 3. For example, if the device displays frequency changes of that, then starting frequency of 0, the following changes would occur. So 0 plus 1 is 1, 1 minus 2 is -1, -1 plus 3 is 2, 2 plus 1 is 3. So the resulting frequency is 3. Other example situations, for example, whatever. Starting with frequency 0, what is the resulting frequency after all the changes in frequency have been applied? So basically it just wants you to total all of the numbers in the input file. The input file, as ever, is here. As you can see, there are quite a few numbers on this list, in this list. And some of them are quite large. I think there's one quite near the end. Oh, the one last number at the end, +128,917. So let's save this, and then we shall see T21, T01, input text, save it. Okay, and let's start working through this with COBOL. Okay, so I'm already in the right folder here, and path is read only. Okay. Still read only. Media cache local COBOL Advent of Code 2018 day number 1 task 01 part cop. Does this now work? It seems to work. Yeah, now it works. I think it was because I was, some reason I'd created the file as root. I wasn't paying attention when I was using the root user, and then I got a bit confused. Program ID, I'm going to go task 01. Okay. Environment division, input, output, section, file control, select in file assigned to, let's just go straight to input.text, organization is line sequential, so nothing unusual at the moment. Then we get to the data division, and now we have the file section, and let's just save something here, something about the line, fd in file, pick, let's make it something like that, then it's going to be big enough, isn't it? Then we have the working storage section. Let's have the num, which we're working on at the moment. Current num, let's call it num, why not? Just a pick s 96 should do it. Let's have a 01 total pick s 9. Let's go up to 10. Who cares? It's still not much memory. And then we need something to tell us we're at the end of the in file. So let's do that with an in file state. I tend to do it like this. value y, doesn't really matter, any sort of value, in file EOF, value x, any other value, doesn't really matter. Let's go for the procedure division and get the rest of the basic outline working. 00 main, or whatever number you want, open input in file, perform until in file EOF, read in file at end set in file EOF to true, not at end, perform 100 process in file. This is total rubbish I've been writing here, isn't it? This is totally incorrect. This is not the right syntax. We want is something like this. That's the syntax we want to use. Sorry. That's now better syntax. And read, this looks more like COBOL code. Perform. I think we can push these back over. Yep. Close input. And let's just display total. And go back at the end. Okay, let's have a 100 process in line here. So we're going to move inline to num. That should work, I think. What was the largest number we had here? 1, 2, 3, 4, 5, 6, 7 is its maximum length. So S96 should be enough. Okay, sorry. Add num to total. Then we should say total is defined as 0 to begin with. Okay, it's possible this works. I don't know. Let's see what I'm doing wrong. Copy task comp. We need a minus x. And task 01. Expect input window identifier input. It's fine. Open. Close input. Yeah, close in file. It's called. Okay. 437. That could be the correct answer. Let's see if it is the correct answer. I forget. Correct answer is 437. Cool. That works. Okay, that was the easy part. Now things get a bit more interesting. Oh, by the way, if you're interested in things like awk, you can do this really, really well using awk. You can just do a cat for the input, and you can pipe it into an awk. Begin total equals 0. I don't actually need that bit either. And every line you say total plus equals, I think it's going to be the first field in the line, and then at end print total. And I think that's probably all you need to do. Yeah. Which is awk is a really nice tool. It's worth, I think awk is probably for most people worth learning. I certainly like using awk. It's one of my suspicions that a lot of software can be replaced by, well, 80% of software could be replaced by 3 or 4 decent awk scripts. It's a very powerful little tool. And you can see how well it's designed just to do line processing. A lot of the boilerplate code which you have in this COBOL program, or in any program which comes from a general purpose programming language, just to do things like opening a file and things like that, it just disappears, and to go through the file line by line. The shell with the command cat basically does this stuff here without any difficulty, and also this stuff, and the only thing you have to tell awk to do is basically that, and then display it at the end. So if you have a particular problem which can be solved just by going through a file line by line and doing an operation on each line, then awk's really, really good. It can save you a lot of boilerplate code. But of course, if your problem doesn't allow that, then it's not going to be a fun tool to use. So I think it is totally Turing complete. You can do anything you want with awk, but it's not necessarily fun. Let's go to task02.cob. So the second half. A lot of it's going to be the same. Let's just get the basic framework done, basic skeleton done. I could have just copied this, couldn't I? Well, it doesn't matter. It's good practice for me to write it out again. A data division, file section. Just get this right this time. ftn file. That's the first thing you need, and now you define the data in it. In line pick x. What do we say? 8. We said it doesn't really matter much. Then we got the working storage section, and now let's start looking at this problem a little bit better. Because we're going to need to look at this problem a little bit more to understand what to do here. Okay, part 2. You notice the device repeats the same frequency change list over and over. So it just keeps going on. In this case, you've got this very short list, and it keeps going through the short list. But in our case, of course, you've got this very long list. It just keeps going through this very long list. And I'm not sure how many numbers there are in this list. Let's see how many numbers there are, just so we have a feeling of how many numbers we've actually got here. It's input text, and we get 1033. Okay, so you've got 1033 numbers. It just goes through this list of 1033 numbers again. And what it now asks you to do is you need to find the first frequency it reaches twice. So the first time it goes through the list, maybe it'll reach the same frequency twice the first time it goes through the list. Maybe it'll need to go through the list again. Maybe it'll need to go through the list again, etc., etc., before it reaches the same frequency. And this is where things got a little bit interesting, because in the case of the particular numbers which I was given here, I think it had to go through the list 138 times. And you've got to remember which numbers have already been seen. So a naive way of doing this, if we go back, so a naive way of doing this would be say, well, let's just have a list of 9, 15 plus 9 is 24, 24 minus 14 is 10, 10 plus 13 is 23, 13 plus 23 plus 15 is 38, etc. And what you have to do with each number you add to this list, the next one will be plus 10. You have to say, okay, the number's going to be 48. Has the number 48 appeared before? Well, 48 is not equal to 9, 40 is not equal to 24, 40 is not equal to, etc. So it hasn't appeared before. We can carry on. Next number is minus 16, which would be 32. Has 32 appeared before? No, it hasn't. That's at 32. Next, minus 5 would be 27. So 27 appeared before 27. And so what you do every time you get to a new number, plus 2, the next number is going to be 29. So you have to go through the whole of the list, comparing the numbers. And this list grows and grows and grows. And as I said, I found out when I did my solution to this that it took... it had to go through the list. It's a list of 1,000 numbers, 1,033 numbers. It had to go through the list, I think, 140 times before it found the first number, which was repeated. And if you're going through this whole list, checking each number repeatedly, checking each number every time you want to add a number to the list, you've got this running total, so you can get the next number. You know the next one's going to be 29, the next one's going to be 37. That's quite easy to know. But to check if it's been in the list before, you have to go through the whole of the list each time, which means it starts to get really, really slow. And of course you need quite a large amount of memory as well. And beforehand you don't know how much memory you need to know, you actually need to have, because you don't know how long this list is actually going to get. And this is, for COBOL, it's a bit of a problem, because COBOL doesn't have memory allocation when the program is actually running. So you need to get quite a large amount of memory in order to solve this problem. But one of the other problems is, well, going through this list every time. You can imagine this list at the end being 100,000 elements long, and every time you want to add a new element to the list, you have to compare 100,000 times. And this is where you have data structures, so you can say, well, let's just start with one number, and if it's smaller, we know this number's in the list 9. And now look at 24. Is 24 larger than 9? Yes, it is. Well, let's go to this. Let's go to a sort of a left branch and a right branch. And every number larger than 9 is in the right branch. So you start with the 9. This number here would be 24. Would be the next number you'd add, and it'd be on the right branch of 9. And the first number on the left branch of 9, I don't know. Let's just carry on. So 24 would be here. And what number? And then you try to find the number 10 in the list, and you can gradually build up a tree structure. So 10 is larger than 9, smaller than 24. So you save 10 here. 23 is larger than 9, smaller than 24, bigger than 10. So it's 23 here. And you can gradually build up a tree, which has the advantage of lessening the amount of comparisons you have to do, because there's lots of comparisons you then don't have to do. For example, if you want to find the number 38, if you want to see if the number 38 is in the tree, check if it's larger than 9, larger than 24, and is there a number larger than 24 already in the tree? No, there isn't, we just add it here. And you don't have to worry about comparing it with the numbers 10 and 23 if you have this tree structure. And you can show mathematically that the amount of time you have to spend looking for a particular number to see if it's in a tree, it gets proportionally less than going through the whole list. The larger the list, the longer the list, the better this method gets. And there are certain things that have to be fulfilled for this to be a good method. For example, if the numbers were already sorted and you only had positive numbers here, then of course you would never find a frequency, which is mentioned twice. But you would also have to check every number with every other number. So just have a simple, naive B-tree implementation isn't the best way of doing this. But one thing we can do, just to show you how this works, so let me just do this once quickly in Go, just to see what we're sort of looking at here. So let's do task2.go. And we'll see how this works. I don't have anything. Don't have a Go mode. Okay. Let's do everything with this format then. Func main. Let's see how this works. So we're going to have to get an IO, find a way to read the file. B error is gleich IO. What's it called? Is it IO control? No, it's not. It's called something else. Dot read file input. We need those. Input text. If error not equal nil, we're going to have a log.fatal error. It would be nice to have a Go mode in Emacs. I'm afraid I don't have it installed. Let's add the log as well. Okay. It's not IO control, it's IO. It's a sort of IO helper library. Let's just find it quickly. Go lang read file. What's it in? IO util. What? IO util, it's called. Okay. I'm so used to IntelliJ telling me this stuff. Fatal error. And then you just read this into a nums. Get the list of stras is equal to strings dot split string b. That'll do it. For str in range nums nums range strings. Let's now split the let's now transform each string into a number. ioconv dot struconv it's called. A to E. I think it's just we need strings. We need a string conv here. A to E, and we're just transforming strings dot trim space of str to that should do it. If error not equal nil. So this is the COBOL code, which basically just has a move operation. We have to use the string conv a to E to do this using Go. Log.fatal error. Okay. There's something else we need to do. If str, I don't think we have the. Let's do a strings.trim here. Then we'll get rid of this the white space at the end of the line. Okay. Then we don't have to worry about dealing with white space here. Okay, so now we should almost have that. Nums equals append nums num. Okay, so now we've got the what is okay, you now happy Emacs? Cool. So now we've got all the numbers in a list. Let's look for frequencies. So let's have a freak map. Freak is freaks is equal to make map of int to bool. This is basically a set. This is how you do a set in Go. You've got this map of integers to bools, and we're now going to check to see for. Let's just do one infinite list for num in range nums. Let's have a total here. Total plus equals num if fricks total, then format.printf repeated frick found, and let's just print it out, and that would be total, and let's have an exit, so return no point continuing once we found the answer. Otherwise fricks total equals true. Okay, and that's all we need to do. That's the whole task in Go. Let's see if we got this. If we can get this to run. Go run task. Where are we? It's not included if it's import. See how long it takes to get this to run. 655 request repeated frequency found. Okay, let's just make sure we see how many loops we're doing here. For loop num. Loop num is let's just put this somewhere else. Let's just use the whole for synchron syntax. Num is equal to 0. It's equal to 1. Loop num plus plus here. Add the loop num here. Okay. Ooh, loop num. Yes, sorry. Once more. Okay, so loop num 139. So we have to go through all these numbers 139 times to get to the answer. You can see how quickly it runs, and I'm also compiling it as well. So let's build it here, and then let's time task 2. You can see it takes 0.014 seconds to do this. So it's enormously fast. And the reason why it's enormously fast is you have, in most modern programming languages, you have this data structure. You've got a map, which works a little bit like this tree, which I was talking about earlier. It's actually much more complicated, how maps work in modern programming languages. Other programming languages, you can have your own map definitions. Programming languages where something's built into the language, or there's default built into the language. Whatever. They tend to have definitions. They don't have things where you can have maps. Or this is how you do a set in Go. Sets are their own data structure in quite a few languages, but they're not in Go. And of course, this doesn't exist in COBOL. There are lots of things here which you just can't do in COBOL. For example, here we have a var nums where I didn't have to worry about how big it is beforehand. I just append. And behind this append, there's probably some sort of allocation going on. And with this map, I'm using the make verb in Go, and what that does is that creates this data structure. So this allocates memory and does something with it, configures the memory so you could be used as a map. And then every now and then I do this, and this adds something to that data. So there's some sort of allocation going on here as well. And allocation doesn't exist in COBOL. So the question comes, well, how are we going to solve this problem using COBOL? Wrong. Let's go back to the COBOL buffer. Let's see what happens. Well, the first thing we can probably do is we can just save all the numbers. So let's have nums here. Let's just save all of them, because we're going to have to go through the list many times, 139 times. So num table occurs, I think something like 2,000 times would be cool. Then we don't have to worry. And let's have a each element is defined as, what do we call it? We said it was a pick S96 was each element. Okay, let's have a num length as well. As well here. Let's just call this a pick 9 4. We know this is actually 1033. Let's do it like this. Just so we have that number. We're going to need it at some stage. Okay, let's read these in first of all, before we do anything else. Let's read these numbers in. Let's do that by open input in file. Oops. Perform until in file EOF. So we need that again. In file state pick x value y 88 in file EOF value, let's call it x, read in file at end, set in file ref2 true, not at end, add 1 to num length, move in line 2 num Okay. Read and perform and close in file. Cool. I'd like to see what we're doing here. So let's make sure this is correct. Display let's do this just to make sure we're actually reading everything in correctly. So cob c minus x task, so it's fine. So 2.cob and task 0, it's fine. Oops. Procedure section, procedure division. Yes, that's quite true. Sorry. That looks good. Okay, so we now have all the data we need. Now we're going to think of how to build up our tree structure here. Our map, our tree. So let's so our frequencies. Let's just call it map. What we want to do is we need to know how many elements there already are in the map. This is going to be important. And we're going to need a large number of elements in this map because we have to go through this list 100 times until we find something which matches. Let's go for 200,000. Sorry, 200,000 elements, which is probably covered by, let's just call it 6 here, map length. Let's go for the map values. And we're going to have to store a couple of things in map values. So the curve is 200,000, 200,000, I think it is. The first thing we have to do is store the value itself, the number we actually want to save, which is a pic S9, at least 6. Let's make something bigger, just to make sure. And then we want to say, what's the next map index you want to look at for this map file if the number you're looking for is smaller than this one. So the next map index would be something like that. Let's have a signal value of 0, which means it's not set. Let's have a same thing for this one as well. Not greater, that seems to be used. It's quite larger. Okay, cool. Now we've got our map set up. Let's have enough place where we can store the current index that we're looking for. And let's have somewhere where we can store our total, of course, which we're going to use the same pic for the total as we have here for the value which we're storing, value 0. Okay, this now looks a little bit more interesting. Let's go down here so we can see what we're doing. So now we're going to have to go through let's do our major loop. Let's call it 200 loop until we're going to have a state duplicate found. And once we've got that, we're going to have to display it. It's going to be where the total is, of course. It makes sense. Let's also find a way to get our loop number. Okay, so we need variables for this. We need a loop num, a pic 94, value 0, start like that. And let's do something else here. Oh, we've got the length, we need a nums index as well, don't we? Let's put the num index, which we're using here, and index pick 9 for, because we're going to need to know this. Okay. Okay, cool. So let's start looking at this this loop thing. What this actually does. So let's perform while 1 is greater, sorry, until 0. This is my way of doing an infinite loop. So this is my infinite loop. I'm going to go through the number input again and again. Oh, 1 and 0 or duplicate found. Oh, I haven't yet written a field for duplicate. I haven't written an 88 for duplicate found, have I? Let's do 01 num processed state. Pick x value n, and let's have an 88 here. Num processed. No, let's not do this. What am I doing? Duplicate found. We want this duplicate found state. So I'm trying to read from my notes as well, and I'm finding it difficult to read the right stuff. Pick x value n and 88 duplicate found is value y. I remember the num process state. We're going to need that, but I can't just say we're going to need it. I want to show you why we're going to need it. So, perform varying n index from 1 by 1 until index is greater than num length or duplicate found. So that's how often, we're now going to be processing the list of numbers. So this outer perform is, we're just going to be repeating processing this of numbers. So this inner perform is going through the list of numbers once. Add num index, sorry, to total. That's good. Move 1 to m index. Let's start with the first item in the map, and let me do a perform process total. So that here, if we put an answer here, then that's okay. So what we're doing here is we're just finding what the new total should be, and then we're going to look at the first item in the map, and then we're going to perform 300 process total. We don't actually need to put this here, do we? This is a little bit confusing to have it here. Let's put it somewhere else. Let's do 300 process total. And let's move 1 to m index here. This is going to be a little bit less confusing. Now we've got to be a little bit careful here. Let me build this up so you can see why we need these various things which we're going to need here. First we have to do is, if the map length is equal to 0, then we have the special case that it's the first version. It's the first thing to be inserted into the map. I'm creating first entry. Add 1 to map length. So map length here should be 0. And then we can move total to val 1 Okay, and if. Cool. This so it looks better. Now, what we now need to do is we have to do the loop, which goes through all of the various, which walks through the tree. And there are various things we need to look at while doing this loop. So let's do a perform until. When do we need to break it? We need to break out of this loop. We need to break out of this loop when we've either found the number or we've stored the number. And in my notes, I call this num processed. So let's add this here. When set to false is n. Okie dokie. So let's, wrong number, wrong thing as ever. Set num processed to false. So we haven't yet processed this thing. We can also add it here, can't we? And if we do it like that, then we can say perform until num processed. Yep, that looks good. Okay. Good. Then we have to we have to check certain things. There are three states which interest us. A number of different states interest us. The first state is we found the number. Is one possibility. So evaluate. Let's just have a look at this. Evaluate val for the current element we're looking at, which is m index. When is equal to the total. Then set duplicate found to true and set num processed to true. Okay, this is one possibility that we're looking for. If we actually find it. What are the other possibilities we're looking for? We're looking for if we should look somewhere else, if we set m index to some other value and go through this perform loop again. This is going to happen when the number is smaller than the val we're looking at and smaller is set, or when the number is larger than the value it's looking at and this larger is set. So let's also add these to our evaluate. Oops, that doesn't fit. Okay, when total also any, cool. When let's see what happens if it's larger than the total. Larger total also not equals 0, also any. So when the number we've stored, the number we're looking at, the value we are looking at in our tree is larger than the number we're looking for, then we check to see if smaller is set. So smaller is not the signal value of 0. If it is, then we just set m index to smaller. And we carry on. Okay. We can move, might be better. Move smaller m index to m index. And we can do the same thing quite simply for when the number we're trying to find is larger than the value. Also any also not equals 0. Move larger index to m index and just carry on with the next loop. So we're not setting num process to true here. We're just carrying on with the next loop. We'll go back into perform until num processed, but mindex will be a different value. It'll be either the left branch or the right branch of the cell of the node we were looking at. Okay, what's the next thing we can look at? What happens if it does equal? If we are trying to find something smaller, but this doesn't exist yet in our tree? Well, we can look at also equals 0, also any. Now we've got to create a new element. We do this by, first of all, adding 1 to the map length. So we're now going to the first free cell in our map file table here. Add 1 to map length. Move total to val map length. Let's put it there. Move map length to smaller, and we're going to store this new key, this new index, in the current smaller. This one which we just checked is equal to 0, and now we want to store it there. And that means we've now dealt with this particular number. That's all we can do at this moment in time. And of course, when less than total, also any, also equals 0, then we do pretty much the same thing. Add 1 to map length, move total to val map length, and move map length to larger index, set num processed to true, and evaluate. That's all we can do, I think. And end perform. And that's actually, strangely, this is pretty much all the program that we need to write. Let's try to get this on one screen, or pretty much on one screen, so we can explain once more exactly what this all does. Okay, this looks okay. We've now got it pretty much on one screen. Yeah, we have. Okay. So let's make sure that it works, of course. Maybe it doesn't work. Maybe I've made a mistake copying from my notes. I probably have. Comp t minus s task comp. I think it's working. Yeah, it's doing something. You can see it really working here. It would be nice to have some sort of output so we can see if it's really doing something or not. Yeah, let's add some output to this. Oh, it did it. Duplicate 655. We don't have the loop number because we haven't been adding to the loop number. Let's add to the loop number each time. Okay, then we can display the loop number there. And let's add something here so we can see which loop we're in. Display, so we can see that it's actually running. And let's try to get this to run again. Okay, so you can see going through 1,000 numbers each time. And it starts by going really quickly. Now it's getting a little bit slower as this tree gets ever bigger. And there's a reason why this is so much slower than the Go code. And the reason why it's so much slower is that we're not balancing the tree at all. But it does get to the answer, which is good. I tried this once, tried this to begin with, naively with just a list, and I got to about loop number 20, and they're just getting so slow. It was taking minutes to get to the next loop number. And this is on a fairly fast Intel processor. So the reason why this is so much slower than the Go code, so orders of magnitude slower, orders of magnitude, yeah, probably, is that this evaluate thing, we're not doing any any sort of tree balancing. We're just adding a node here and here, and we're not trying to balance it to make the paths to each of the possible numbers roughly equally long. You can imagine if you have a long chain of positive numbers in the input, then this tree will have some very, very long branches, very long paths to get to a leaf node, to get to the final leaf node, where you can say, okay, either this number exists or it doesn't, either this number or it doesn't, and then I've got to add it to the tree. And there can be some very, very long paths, and some paths are very short. For example, to check for the number 9, which is the first number in the list, that's a really, really short path, and other paths are just very long. And this is because we tend to have things like buckets. We're not trying to distribute the numbers throughout the tree so that the paths are as short as possible. Instead, we're just adding them anywhere we want. Adding them to the tree without worrying about balancing. So this is still an awful lot slower than the Go code, but it does actually work. And if you just do the naive approach of putting the numbers, putting the frequencies, putting these totals you get to in one long line. So with 9, 24, 10, 20, 33, 48, just in one long line. This doesn't work at all. You won't get to the answer before the universe dies. So yeah, it's already pretty useful and a lot better than just having one long list. And even if you sort the list, you could do it by sorting the list, couldn't you? But then you'd have to spend the time sorting the list, and that also take quite a bit of time just to sort the list. You could think of having a sorted list of totals, and you'd have to add elements to this sorted list of totals somewhere, and that would be just quite an annoying thing to do. But that moves a little bit towards things like balancing strategies. Anyway, this video is now long enough. I thought it would be quite interesting to show you, and hopefully it's interesting to someone. And talk to you soon. Bye.